Okay, so today we're just going to finish up on the set theory stuff. So far we've talked about definitions, operations, and stuff like that. So there's a couple more things I want to introduce today. And then we've talked kind of briefly, I gave you guys examples of sets, and I said, okay, maybe for the natural numbers, we have this really like hand-wavy way of like, saying, oh, 1, 2, 3, blah, blah, blah. But I've also kind of contradicted myself because I said before in the previous lecture that, well, we can't just know what numbers are, right? There has to be some way to get them. So far, the only thing that we know axiomatically is that there exists an empty set. So before we go into that, I've talked a lot about axioms and axioms being stuff that are allowed to know. I'm not going to go very deeply into what the axioms are in set theory, but for example, the language we've used so far, the grammar we've used so far is stuff we get from propositional logic. The vocab and the definitions that we're going to start developing starting from set theory has to come from somewhere. And so these are what some people call the Zermelo-Fraenkel axioms. And sometimes people refer this to ZF. So what are these? I'm not going to write all of them out, but essentially, there are things that tell you how to move from propositional logic to set theory. And a lot of stuff I gave you guys last time in terms of definitions come from some of these axioms. Like, for example, I told you guys that there was a connection between, two statements, maybe statements P and Q, right, in propositional logic versus maybe the union of two sets, right? But so far I just said, okay, we'll define it this way, but how do we know this exists? We don't know beforehand that it has to exist. So one of the axioms, for example, of Zermelo-Fraenkel tells us that there does exist a set such that X is in A or X in B for propositional logic gives us this A union B. So they'll define a union a certain way. We'll define a union as something like this, right? I don't want to go too deep into the details because they do get a bit hairy and they do get a bit convoluted, especially for people who haven't really seen math before. If you are interested, I'm more than happy to talk to you personally, or maybe we can do like a separate Zoom office hours specifically for just Zermelo-Fraenkel axioms. But basically, just think about it as all the stuff I've been talking about and defining has to come from somewhere. They come from this ZF. So if you look them up, you will see a lot of stuff like the intersection, the union, stuff like that. The most important one I want to talk about, though, is the empty set, right? There exists a set called the empty set. Now, this is really bad notation, but I think this is just good, like shorthand, is technically there exists a set that is empty. Right? This is one of the axioms. There's something called the empty set, and it's exactly what we defined it as last time, as just a set with nothing in it, right? That's the only thing we concretely have, right? We don't have number one, we don't have letters, we don't have anything else. The only thing we have is the existence of the empty set, right? We're told that this set exists. And what we're about to do is we're about to take this empty set and we're going to construct other things out of it. So kind of before that, maybe a good thing to know that I didn't include last time is let's just have a quick definition here just so that we can use this later on. Right. The cardinality of the set. So let's say the set is called capital S. And this has been noted with absolute value signs. Is the number of elements in the set. So we start with this because you kind of know what numbers are, and I'm going to go with that for now. Once we're done with this whole treatise that I'm going to give you guys on the natural numbers and constructing them using empty set and so on and so forth, we'll come back to this definition and see how we can make this make sense using the language we have. right? Because if I want to be really strict and really nitpicky, I can say that, well, isn't a good definition because I don't know what a number is. I don't know how to count yet, right? I have no way to do any of these things yet. So maybe this isn't a good definition a priori, but like this should make sense to you guys right now, just from what we do know from previous math class, right? We know how to count. So if we have a finite set, we can count the number of things in that set. And if we have an infinite set, well, we just say the cardinality is infinite, right? We have finite sets and infinite sets, and that's all well and good. But I wanted to define it this way because we'll kind of see how this works. Just as a quick aside, some of you might be wondering, wait, did I just use the absolute value signs? What's going on here? Well, I do. We mathematicians end up using these bars a lot, right? So for example, we have it in absolute value signs. We have it in like cardinality. We even have it for like two-dimensional stuff. What they really mean is they're really talking about the distance. Right, so whenever you see the absolute value, instead of thinking about an absolute value, think about it as distance. Again, this is something we'll take more of a look into when we talk about real analysis. But for example, we all know that the absolute value of 5 minus 3 is the same as the absolute value of 3 minus 5, and that's the number 2. Well, I said distance, and distance has a geometric mean. So what this is if I draw a number line, and I have numbers 3 and 5, this absolute value represents that the distance between these two numbers is 2. Right? So it's a way to measure something, right? If I want to measure something about this interval or something about these two numbers, I'll measure the distance between them. Just like if I want to kind of measure a set, well, one way in which we can think of measuring a set is see how big it is, right? The size of the set. And sometimes you'll hear people use that to talk about cardinality, right? People use the size of the set to talk about cardinality. Some alternate notation that you'll see in some books. You might see size of the set, right? Just like we said. You might see NS, where the middle N refers to the number of elements in S. These are some other notations that you'll see for people when they're talking about the cardinality. There's a really weird notation. I've only seen this in 2 books. It's like an S with a double bar over it. I have no idea why they use this, but I've seen it in a couple places. But at the end of the day, if a book's using any notation, even if it's obvious notation, they'll usually define it first, right? So if you ever see a symbol that you're not used to, instead of thinking like, oh, what is this? It's new to me. See if you can find where they define the notation in the book. But so the only reason I want to talk about cardinality is now we can talk about how many things there are in this set, and maybe we can use it to kind of discuss why, what I'm about to do makes sense. So far, let's take 2 things and put them together. The first thing is we have an empty set. The second thing is I told you that the set containing the empty set isn't the same as the empty set, right? Like containing sets within another set, even if you're not adding any extra elements, you're changing what it is. So maybe, what is the empty set? It has nothing in it, right? And if we want to kind of define numbers, maybe 0 is the most natural number at which we want to start, right? Maybe we want to start counting at 0 in this case. So obviously this is the number 0. I'm going to treat it as a symbol that we haven't defined it, right? So imagine you're at a point where we're building math from the ground up and you have no idea what a number is. All we have is the set theory stuff that we're talking about, right? We can make sense of what it means to put things together, but we have no concept of numbers. So we're going to start by defining 0 as, this is defined by the empty set, right? So we're going to treat these numbers as sets instead of numbers. So what's one thing we can do here? Well, I can do this, and I can say that this is the empty set union the set containing the empty set. Right. And so when I take a union, if I have nothing over here, and I take a union, well, it's going to remain the same, right? So this is really equal to the set containing the empty set. So we talked about how these 2 things are different, right? This is a set with nothing in it. Whereas this is a set with one thing in it, right? I have an empty set in here. So even though this is a set containing an empty set, the overall set is still a set with one element, right? In other words, whatever this symbol is, the cardinality of it, if we know what numbers are, is 1. So there's kind of a natural idea between the cardinality, even though how we're counting, versus what we're calling this set. So as you can imagine, if I continue this with a pound, right? Let's say 1 union the set containing 1. But what is 1? 1 was the empty set, right? We union it with the set containing the set containing the set. Right? You can see how that kind of works, right? If I want to rewrite this, I can almost have something that looks like this, right? I have a set with one element here. I have a set with another element here, right? So if we go back to like what we were talking about yesterday with basic, unions, if I said you have a set A union a set containing B, this is just equal to the set containing A and B, right? Like just taking unions. Well, let's just call this A. And let's call this B, right? Here's my A comma B. Okay? So we can define it that way. And now this set has cardinality 2. There's 2 things in here. There's the empty set and the set containing the empty set. So obviously, if we keep going on, this whole set containing the set containing this empty set, comma, set containing, that's going to be ridiculous to talk about. So we're just going to do what we call defining this inductively. We'll talk about induction next week, but really, whenever you hear someone says that we're going to do something inductively, that means that we're going to follow a pattern. We're going to start by having a rule where we know what we do at the first case, and we're basically just going to climb a ladder, right? We're told that we can start on the ladder, and we know how to get to the next step, but we're going to just keep doing this, right? How do you get from one step to the next? You put your hand on top, and then you put your hand on top again, and you keep going, and you just keep going. It's a repetitive process. We're going to call this kind of process of induction. And I'll talk about it more next week when we talk about proof techniques, because one of the proof techniques we'll run into is proof by induction, right? And for now, we're just going to stick with this. Okay, so what is our rule then? As you can see from here, maybe if I have a set, let's call it little n, right? Maybe we can say that little n plus 1 is defined as n union set containing n. And now we don't know what plus 1 is, right? We haven't defined a plus. So maybe we can even go one step further and we can say, instead of saying n plus 1, we can call this something like capital S n, right? This is what we call a successor function, right? Successor means it succeeds, right? It comes after it. So here, this is a very common thing to use. This is a successor function that takes n and says what happens next, right? What's the succeeding term? Well, the next term will be whatever that term is, union the set containing that term, right? So what do we end up getting here? We end up getting that 0 is an element of 1, right? We're not saying 0 is less than 1. We don't know what less than is. We're defining numbers as sets. So when we're comparing sets, we can say something's an element of, or we can say it's a subset of. So in this case, the empty set is an element here. The set containing the empty set is an element over here, and so on and so forth. So each natural number, we kind of have a chain where they're contained in the next one, right? But look here, 0 is contained in 1, but because 1 is a union of what came before, well, 0 is also in 2, right? It's right here. This is 0, and this is 1. So now that I have this way of defining numbers, let's rewrite this in a more succinct format. right? One is just a set containing 0. 2 is a set containing 0 and 1. And you can kind of see where this is going, right? 3 would be the set containing 0, 1, 2. N, right? Maybe the successor of n is the set containing 0, 1, 2, all the way to n. Right? And maybe we can define this to be, hey, successor, we'll define it as, oh, it's n plus 1. Right? So maybe whenever I say plus 1, I have some sense of meaning, let's go to the next one. So let's define plus 1 to be the same thing as taking the successor function. Right? So keep in mind still, all of these are sets. We just have a way of thinking them as numbers to represent sets in a way that this all makes sense. Right? And so notice that any set contains is exactly a set of every single element that comes before it. Right? That's not how we define it. It just happens that that's true, taking this definition of the successor. Right? And so it turns out that not only is 0 an element of 1, 1 element of 2, is not just a single step thing. We can actually say that there's something called, so I'll write this as a proposition. We have something called the trichotomy of natural numbers. Right? Tri meaning 3, you hear like dichotomy is a split of 2 things, trichotomy just means 3. This means that for any natural number, right, we'll define this set, this construction, we'll define this as everything in the natural numbers. We'll say the natural numbers are constructed by every set and all its successors, right, all the way to infinity. So not just one of the following things are true, but only one of the following things is true. Or rather, I should say exactly one of the following is true. And what is it? Well, either we have m is an element of n, n is an element of m, n is equal to n as a set, right? So set equality means m is contained, m is a subset of n is a subset of m, and thus they're both. Right. So the trichotomy says when we discuss the natural numbers in the sense as sets, we get exactly what we expect from natural numbers, right? If you compare natural numbers, one's either less than the other, greater than the other, or they're the same, right? There's no other way to do it. But that here comes the proposition straight from the definition of our natural numbers. So the main reason why I wanted to give you this is to show you that there are a lot of things that we naturally know about, and there's a lot of things that we take for granted, right? We obviously know how to count. We've known how to count since we were however many years old, right? We've done it for so long. But this all becomes because people say, oh, here's how you count, right? In math, if you want to think about why we're allowed to do things, if you want to start from only axioms and move up, this isn't axiomatic. This relies on an axiom. In fact, it relies on multiple axioms. It relies on the existence of unions. It relies on the existence of the empty set. It relies on a lot of things that we just take for granted in these Zermelo-Fraenkel axioms over here, right? So we use those to then construct numbers in a way that we have something to work with later, right? So the idea is if we start from a world where we only have sets, in fact, if we start from a world where we only have empty sets and rules about how to construct new sets, well, how do you get numbers? You get numbers like this, right? You get numbers in exactly this format. And maybe, what about negative numbers, right? How would we get negative integers? Well, perhaps we can find a way to get 0 in there, right? We know that 5 minus 5 is 0. But that's the same as saying 5 plus negative 5 is 0. And there's a lot of ways to talk about it, but really maybe the best way to talk about it is set difference, right? We know what a set difference is. It's an intersection of a set with the complement of it is. In other words, if you remember, we have set difference here is A intersect B complement, right, within some universe. And so maybe we can use that to somehow define the kind of things we're talking about. So now let's go back to this definition. I promised you we'd take another look at this now that we've constructed what we have over there. So we might not know what numbers are before, but this is why we talk about counting elements in a set, right? It's exactly related to this, right? Now that we have a way to count, our numbers are defined exactly by the number of things in the set, right? So if two different sets have the same number of elements, then they should have the same cardinality. And so we'll define the cardinality of each of these natural numbers by that number, right? So now we can start moving from a set to numbers, right? So now we've constructed, again, I'll keep stressing this, we're constructing these symbols 0, 1, 2, 3 as sets. And then we're going to use this definition to say, okay, let's call these numbers, right? We'll associate the size of each of these sets with a number which just so happens to use the same symbols, right? So we can freely now use the numbers 1, 2, 3, 4, 5, etc., right? But we use them because there's a way we can construct it from sets, right? We're allowed to do it because we construct it from the axioms, right? There's no axiom that tells us that all these numbers exist. But there are axioms that tell us that an empty set exists, and we can do something with it, with operations that we've defined to put them together, right? So that's how we get the natural numbers, right? So last time we talked about, this inclusion of sets where we get naturals living inside the integers, which live inside the rationals, and so on and so forth. Well, if we want to construct each of these, we need to start at the smallest one, right? We've constructed the natural numbers, right? And then maybe we can include an extra construction to get the integers, right? Including all the negatives. And then maybe we can use that and define division in some way. We don't know what division is yet, but maybe we'll define it in some way so that we get the rational numbers. And then we'll somehow get the reals and so on and so forth, right? So kind of that's the main point I'm trying to make. It's not that, it's not that it matters that you have to know that natural numbers are constructed this way. The point is more that we are required to have this weird construction because we can't take any definition for granted. We have to know where the definition comes from if it's not from an axiom or is not an axiom itself, right? So we're constructing things that we're allowed to do. So because without doing this, the only thing we have is the empty set. So when I talk about things like, oh, the set containing 1, 4, and 5, you can think in your head that if we really want to be nitpicky, we can rewrite that as a bunch of empty sets, right? We can rewrite it as the set containing 1, 4, 5 is a set containing this set, the set representing 4, and the set representing 5. So that would be a set of 3 elements, each of which itself is a set, right? So I know I'm kind of beating a dead horse to death, but that's a very important, not for the content, but more for kind of like the thought process and why we care about having so much detail in that, why we care about, really emphasizing these extra conditions that we get from axioms and going to kind of more detailed, like, hey, how do we get these things? Okay. So one more thing I want to talk about in terms of axioms is, we talk about something called the Zermelo triangle axiom of choice. Everything that we do in set, so all the major things we talk about in math, like when you do Calc 1, when you go on to do algebra, when you go on to do all your other types of math that you do in the standard Korean math, uses this set of axioms, right? There are other sets of axioms. There are other worlds that use different axioms than Zermelo-Fraenkel and give something different. That's fine. But what we use is Zermelo-Fraenkel with something else. That's called the axiom of choice. The axiom of choice is kind of stupid. I'm going to kind of paraphrase it here, but essentially, the idea is if I have a bunch of boxes, the axiom of choice tells me I'm allowed to pick one thing from each box, right? Or if I want to be even more specific, even if I have a bunch of boxes, an infinite number of boxes with infinite number of things in each of them, I can still pick one out, right? And it sounds really dumb because it's like, okay, this just amounts to saying is, what this amounts to saying is if I have like a bowl full of like a bunch of balls, I can just pick one out. That's literally all this is, right? But it ends up being important because there's a lot of things we do in mathematics where we just assume we can pick something out. And sometimes we can't, right? You can almost imagine a world where sometimes because things are kind of stuck in there, you can't pick one out, right? So for example, we might not know. So okay, so maybe this is a good example, right? Like maybe I'll use a stupid example. Let's say you have like a bowl of candy that are in their wrappers, right? And you can just pick one out if you want to. But what if I have a bowl of candy and without the wrappers, it's a hot day and they start melting into each other? Now it's possible that when I try to pick one out, it won't come up as one. It comes up with a whole bunch of other stuff. Now, the analogy to mathematics is that there are some cases where, for whatever reason, axiomatically, we can't determine the difference between certain elements, and when we take one out, other ones come along with it. And that's why we need this as an axiom, right? We need to state that, okay, we need to be able to somehow denote that, right? So for example, in the candy example, if they're all melted together, I can still maybe find some way of drawing. I can remember what the shape of the candy is and maybe draw what that looks like and say, okay, this portion of this conglomerate melted piece, that was what the original candy was. I can like separate it from the rest of it, right? There's something like that we can do. That's what the axiom of choice gives us. It allows us this way of knowing what one object was, right? So when you put these two things together, you get very originally something called ZFC. Right? So if you ever see people say ZFC, they're referring to the Zermelo-Fraenkel axioms with the axiom of choice. And this is the set of axioms that we generally use for our set theory, right? When we construct the real numbers, when we use all these sets in Calc 1, when we teach about sets in college math, and so on and so forth, this is all assuming ZFC, right? There do exist other schemas. There exist other types of ways in which we can define a world without the axiom of choice. For those of you who are curious, there's a lot of mathematicians who dabble in what's called voting theory, where it really is what you think it is, right? You study the politics of voting, but there's also some mathematics behind it. It just so happens that when you're discussing voting and counting votes and stuff like that, and deciding who the winner is and whatnot, when you're doing that from a mathematical standpoint, you can't use the axiom of choice. You end up having to use what's called the axiom of determinacy, which is directly contradicting the axiom of choice. Right? I won't go into that, but there do exist, even though I say that everything we do uses the axiom of choice, there do exist cases, actual real cases where people do important work that doesn't assume the axiom of choice. And this is why I'm always stressing this, you have to know what axioms you're starting from. Even if you're doing a lot of set theory, and you don't know that using the axiom of choice, it's important to know that you are using it in some way. There's a lot of people who will get to grad school, and in fact, most people who will get to grad school in mathematics and have never used the axiom of choice. Maybe they've heard of it, it's something that comes up in a lot of pop math. A lot of people make fun of it too, because it's such an obvious statement that seems like you don't need to define it. It's just clearly something you always do. So a lot of people make fun of the axiom of choice, myself included. But the idea is that a lot of people just don't know the formulation of it. And this starts being a problem when you get to more complicated mathematics. There may be some cases where you don't realize you're using the axiom of choice when you are. And so your argument kind of falls apart because maybe two statements will sound like they both make perfect sense, but one made perfect sense because of axiom of choice, and you're using it without realizing. And the other statement still makes sense, but didn't actually require the axiom of choice. Right, so it's almost like you're invoking an extra condition without realizing. So that's why we want to talk about not just ZFC in itself, but just axioms. Right? This is why axioms is so important, and I'll always reiterate that you need to know what your axioms are to see where you're going to go with it. So I'm going to cover one last thing in set theory that I probably should have covered yesterday, just to make sure. We didn't talk about, so I mentioned briefly properties in propositional logic that we can kind of like see, we have distributive laws and other laws and stuff like that. Those exact same properties can move over to set theory, and maybe we should see what some of those are, right? So sets are under the union and section operations. the commutative. This means that for any two sets A and B, this would make sense. Right? If I'm just comparing two sets and I'm drawing a Venn diagram, it doesn't matter what I label it as, the union is going to be the same, the intersection is going to be the same, right? There's no difference when I compute this. So associativity does not hold in general. Right? So maybe you can think of something like A union B intersect C versus A union B intersect C. These would distribute in different ways, right? This, as you remember from our distributive laws, which I'll write out again later, this distributes as A union B intersect A union C. But this is A intersect C union B intersect C, right? So we have to be careful about associativity. Now, if all of these are the same direction, if they're both intersections, then sure, we have associativity. If there's a bunch of things union together, we have associativity. That's one way in which we have stuff like that, but we have to be careful in general, right? So I would instead say that associativity holds under the same operation. Okay. Now, let me maybe say that it's like A and B sets. We talked about that being a universe, right? There's a big universe from which we get our sets, where these things are allowed to live. It should make sense that A union the whole universe should just give you back the whole universe, right? You're taking everything and just keeping it here. A intersect the universe. A, right? Because A lives inside the universe. It's almost like A is a subset of the universe, right? We also have that A union A is same as A intersect A. Now, I want to just remind you guys that these aren't definitions, right? Our definitions lie in how we define these properties. These come from our definitions of sets, right? So it's not that I'm defining these two things, these three things to be the same. I'm saying that they happen to be the same because of how we define these operations, right? But this identity law should make sense, right? If I take this set and union it with itself, you get it's obviously the same set. There's nothing else to add or remove. Maybe one other thing. So I'll maybe write the distributive laws over here, but oh yeah, I should mention this. We have to talk about the empty set as well, right? So maybe another one is a set union empty set. I'm not adding anything, right? Just A. Intersect the empty set. That's equal to the empty set, right? There's nothing else in there. If I'm taking the intersection of A with nothing, right? They don't meet up anywhere. And then maybe we can talk about distributive laws. So this is maybe A union B intersect C. You have the same thing for these going to be other way. The last thing I'll probably add here is one that we should all be familiar with from De Morgan's laws, from propositional logic. That's this, right? When I distribute a complement, it flips everything, including the sign. Right. And same here, if I have A complement intersects right? So these are some properties of sets that we should be okay with, right? These are all things that come out of just the strict definition of our operations, but there are things that just always hold true. Okay. So that's pretty much all I wanted to cover. Obviously, there's a lot to cover in set theory, but these are kind of the main things I want to talk about. Maybe one definition I'll give that will come up later. Maybe this is a bit disjointed, but I won't go too much into it, right? We can say that sets A and B are called disjoint, or sometimes we'll hear the phrase mutually exclusive. If A intersect B is empty. Right? In other words, when I draw them as a Venn diagram, they don't have an intersection. The intersection is empty, so they're just separate, right? So it makes sense to think that disjoint from each other. Some people will say mutually exclusive is a term you'll sometimes see in a lot of introductory set theory or even probability classes. You'll hear mutually exclusive, but really disjoint is kind of like the term that a lot of mathematicians use, especially when talking about sets within like analysis, analytical theory, stuff like that. You hear disjoint as a word more in more advanced settings than the word mutually exclusive, right? But essentially, yesterday's lecture and today's lecture serve to introduce set theory, not just as a way to show you where we build things from the ground up, but it also shows you a way that we can think about, okay, if I want to describe my objects, I have to start from somewhere. And sets are the easiest way to describe objects, right? Every time we've mentioned, oh, this is a real number, that's a natural number, or this is an integer, we're really talking about sets without perhaps realizing it, right? Because the real numbers form a set, the integers form a set. What we're really talking about is all these things are sets within sets that we're considering, right? So we kind of just I kind of wanted to just go through the language to talk about sets, right? That's why we talk about set order notation. It gives you a way to represent sets without being too informal, or it kind of just uses propositional logic to kind of help define what you have. And then we have all these properties that we can use to distinguish sets or relate them, and so on and so forth. So far, you will definitely find that there's a very easily seen connection between what we've discussed in the last 2 days versus what we discussed in the first 2 days, right? Between propositional logic and sets. It's a very natural progression from taking everything in logic and taking it one step further and moving it into sets, right? But now that we have sets, we can do a lot more. Right? So I think I might end the class a little bit early. There's a little bit more I want to talk about, so maybe I'll just say a couple more things about proof techniques. We haven't really developed enough definitions to really do proper proofs that would be helpful, because I could give you a few proofs to do right now and go through a few of them, but currently a lot of them would just be like playing around with the order of operations or playing around with truth tables and stuff like that. And those I think are more computational than proof-based, right? Now, having sets, maybe we can start proving things about numbers, right? In every intro to proof course, the first proofs you'll end up seeing is like, oh, prove that the square root of 2 is irrational. Prove that if a number is even, then its square must be even, and so on and so forth. There's a lot of proofs like that, but those will require a little bit more machinery and a little bit more definitions, which we'll get to next time, right? So let's just go over the generic types of proofs you'll see, right? And then we can keep these in mind as we move forward. So a lot of classes, so when a lot of people teach inter proofs, they'll kind of like give you a whole bunch of definitions that they'll throw at you, and then they'll just go one by one through proof. So they'll maybe do like 3 days on one proof technique and then another 3 days on another proof technique. and they'll introduce them one at a time, which I don't really like. I would almost prefer that you see what our arsenal is, like basically see what we're allowed to use, and then we can sort of build an idea of when we end up using them, right? So I'm gonna just give you guys an idea of the main proof techniques that we use. Right? So here are the types of proofs that we use in this course. Direct proof, which literally just means you just prove it directly. It's nothing fancy, you're just doing it exactly as is on paper. Right? So when we're proving something, it's not just a single statement, right? It is not just like, oh, A and B is true. Like it doesn't really give us anything, right? If it's true, it's true. If it's false, it's false. What we want to prove is implications, right? We want to say, hey, if I have a bunch of these things, can I show that these other things are true, right? So proofs are usually a rephrasing of some implication or conditional statement, right? You're really proving a condition. You're proving that A implies B somehow, right? So maybe I'll do it this way. So for all of these, I'm going to show you how to prove A implies B, right? And so for direct proof, maybe I'll say this column will be the symbol we're trying to prove, the symbol or statements. And here we'll talk about the formats. Right, so here direct means we just immediately prove A implies B. The format will be, you assume A is true, and we show that B is also true. Right? We'll assume A is true. A gives us something, but the only things we're allowed to use are the things about A, and the things that are true because A is true. And then using that, we'll maybe put that together somehow to show that B is also true. We have a proof by contrapositive. We talked about this a little bit in the past lecture, but we've shown that there's a logical equivalence between A implies B and not B implies not A. Right? This is the contrapositive statement. So in other words, negate B and negate A. When we talk about negations, right? We talk about how to negate a statement. So we have a statement B and we have a statement A, rewrite them using the logical connectives and the quantifiers, and then negate it the way we talked about. Then we do a direct proof between those. Assuming negation of B and showing negation of A, right? So this is just a way of reformatting it. If I'm starting with A implies B, well, let's just look at their negations and then just do it the other way. We're just doing a direct proof of the negations just going backwards. Right? That's a proof by contrapositive. Proof by contrapositive. Here we have a proof by contradiction. And so here's the idea, right? A implies B, we said, is logically equivalent to the negation of A and not, right? And for those of you who might not remember this, you should think about the truth table, right? The only time this statement is false is in the row where the hypothesis is true and the conclusion is false, right? Any other time it's true, that's why we put a negation. So what does this tell us? Assume A and not B. Notice that there's no implication here, right? I'm just assuming that A is true and B is false, right? Assume that's the case. Then you do some work and show that something terrible happens. It all fails. Nothing works. Right. So maybe this might amount to something like, if you assume that A is true and B is false, you can do some math and show that, oh, 0 equals 1. Well, 0 obviously does not equal 1, so this thing is false, right? But, so that means that if this is false, then the negation is true. But this is logically equivalent to the implication. So A implies B is true. So this right here is just to show you the format of how you would think about it and why a proof by contradiction works, right? We've used these logical connectives to show that, okay, if I can write this and rewrite it as A and not B, then if we show this is false, the negation is true implies that the original statement must be true, right? But in reality, when you do a proof by contradiction, it always kind of works a similar way, right? You're literally given A and B, you say, okay, assume A is true, and then you negate B and assume that's true, right? And using those, you put them together, you work with it somehow, and you get, oh, crap, it doesn't work. So therefore, it's false, so the negation is true, so the original statement is true. And usually the way we write this is like, we'll say assume for the sake of contradiction, that's blah, 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 right? That this statement is true. And at the end, you would say, okay, once you get to something like 0 equals 1, you say, okay, thus we have a contradiction. And so because of this contradiction, our original assumption was false. And so our original statement is true, right? That's how we work. And we'll see this later on. So don't worry if I'm not writing any of that down or whatever. We'll get back to that later in more detail, but that's just a general outline of how we would do that. Let's see. And we just tell people, like usually we'll tell people how we're going to prove things. Like we don't have to, obviously, because if people read through our proofs, they'll know how we did it. But if it's direct, you don't have to say anything. But usually, if you are proving something by contrapositive or proving something by contradiction, it's considered polite to tell people you're going to do that, right? Like I'm going to say, hey, by contraposition, I will prove that blah, 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 or it's enough to show that blah, 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 right? They're not the same statements. But if you just remind people that you're using contraposition, they don't have to think too hard to see that what you're proving is a contrapositive, because if A and B are really, really complicated statements, seeing the negation might not be obvious. So sometimes when you do a proof, especially if it might not be obvious what you're doing, just say what you're doing, right? You're doing by contraposition, say you're doing by contraposition. If you're doing by contradiction, say you're doing by contradiction, right? That's why in a proof, I always say, I use some term like for the sake of contradiction, right? This is a very common acronym in math because people use it all the time, right? I'll tell people it's contradiction, so people don't get confused by reading through my proof and going, wait, that's wrong, 0 equals 1, what the heck's going on here, right? So saying that we're proving something by contradiction reminds people that we want a contradiction, so something's going to go wrong here. And sometimes it's good to write that just to remind yourself that that's what's going on. The last one doesn't really have symbols or format. This is what I was talking about earlier today, the proof by induction. And a proof by induction, let me kind of outline this for you, works like this, right? I have a statement, maybe show or prove that some statement here then is true for, maybe not for every n. So maybe I just want to say some statement is true for some natural number. I fix the natural number and I want to say that's a true statement. I can say for every n, I want to avoid that for now. There's some issues there that I don't want to come across until we actually talk properly about induction. But the idea is there's two steps. Base case is whatever your starting point is, right? So maybe if I tell you that, hey, let's see, n squared is greater than or equal to 2n for n greater than 2, right? Because in the case where n equals 1, it's false. It's only when n equals 2 where it starts being true, right? So I want a base case, I want a starting point. And we'll talk about this later as well, more formally. The base case, the prove the statement for the smallest possible n. And then we have what we call an inductive hypothesis. Right, and this is what we want to prove, right? The inductive hypothesis states that P of k maybe true for k being a fixed number greater than or equal to n. Right, maybe I'll call this n0 just so you know it's the smallest one, right? So in other words, the induction hypothesis say assume it's true for some kth term. We don't know what k is, it's just a number bigger than n, right? And it's arbitrary, right? Then our inductive step is to show that if the kth version is true, then the k plus 1th version is true. So think about it this way. I have a ladder. And this first rung is n0. So what the base case tells me is I know how to step onto my ladder, right? And what the inductive step tells me is if this is my k, in other words, if I'm already hanging on one part of the ladder, I know how to get to the next step. I might not know what comes in between, but I'm saying that no matter where I am, I know how to climb up. So let's just start at the bottom, right? I know I can get on here. And then my inductive step tells me that I know how to get to the next one, and then the next one, and the next one, and so on and so forth. This tells me I can climb the entire ladder. Maybe I might want to climb up to the millionth step or the 100 billionth step or whatever, but I can always climb up to it, right? Infinity is not a number, so we don't need to talk about climbing to infinity. But this case is why I said for every n in naturals, right? If I fix the natural number n, I can get there. No matter how big of a number you give me, it's going to be finite because you're picking a number, right? You're picking a natural number. The set of natural numbers may be an infinite set, but as long as you pick a number, it's a finite number. It stops somewhere. So what we call this is, we then end this argument by saying by the principle of mathematical induction, or the PMI. And this is something you hear a lot. We'll talk about it later. Maybe when we talk about this in a future section, I'll discuss what the principle of mathematical induction is, but it's also not that important. It's really the most important thing for you guys to remember is that when I invoke the principle of mathematical induction, it's just a really fancy way of saying, hey, this works. And this also comes from one of the axioms of Zumelo-Frankel set theory, right? Because one of the axioms also gives you something about induction using the natural numbers that we created earlier. And it's like, if it's in one of these sets, it's in the next set, and it's the next set, and so on and so forth. So by finishing this, so by the principle of mathematical induction, right, P of n is true for every n greater than or equal to n0, right? This always starts at where your rung is. Even if you know the statement is true for any numbers below that, if you didn't prove it as the base case, you can't start there. Because your base case tells you where to start stepping on the ladder. And then your induction case lets you climb the ladder, right? So that's the idea of induction. And induction is hard. It's hard to see at first just because it feels like there's so many moving pieces. But once you get the hang of it, every single induction proof looks the same. The base case is typically easy to prove because it's just a quick computation. This will use the fact that the induction hypothesis is true. This is why a lot of people screw up induction is they'll get confused on how to show this because they'll forget to use the fact that P of K is true, right? And there's a lot of different types of induction that we can talk about, like strong induction, weak induction. We'll probably have a whole day on induction at some point, but this is the general idea, right? We start with an inductive hypothesis and then we move to the next one. And by the way, this being true, right, is for an arbitrary K, as long it's an arbitrary fixed K for N0, and then we're just showing the next one is also true, right? So because this implication, along with this being true, tells us this has to be true, right? Because there were in the truth table for the implication, there's 3 different parts where the implication is true. But in only one of them was the first one picked to be true. So as long as we pick this one to be true, the second one has to be true as well. And that's how we get the implication, right? So these are the 4 major proof techniques that we'll see, right? Pretty much everything that you guys are doing will be like this. You'll hear some people talk about proof by cases. That's just kind of a subcategory of direct proof, right? You might write a direct proof and the easiest way to do that is split it into cases. Like if you want to prove the statement A or B, then, or say you want a statement, if A is true, then B or C is true. Well, I can do cases. Let A be true, and then show that either B happens, and if B doesn't happen, C has to happen, right? So you can do proof of cases like that, but that's still a direct proof. So we can talk about some of those ways to do it. And a lot of times what we'll see is I'll give you guys examples and give you guys questions, both in lecture and in homework, and we'll start to see some standard ways in which we choose how we prove things. And as you go along in your mathematical career, it's good to be creative and good to have problem solving and figure out how to attack a problem that you haven't seen before. But more often than not, you'll be surprised at how often it comes along where you look at a question that you've never seen before and you go, oh, I've not seen this before, but I sort of know what to do because you've seen similar enough problems and you kind of know what to choose. Proof by contradiction for now, as you're starting out math, like usually don't use a proof by contradiction unless it's your last resort, or if it's the standard thing to do, or if I tell you, hey, use a proof by contradiction for this. Right? I'll try to be careful, no promises, but I'll try to be very clear on when you shouldn't use proof by contradiction or should use it. But the reason it's a last resort and the reason you shouldn't do it until you're more familiar with mathematics is you can get very confused in these steps. Once A and B start being really large statements, taking a bunch of negations here sometimes gets pretty confusing, right? So that's why we want to kind of avoid that. It's easier to do these other 2. It's obvious when you should do proof by induction because it's when you're proving something about, oh, for all natural numbers, this statement is true. That's just obviously an induction, right? Whereas these are more like for implications, if A, then B. So we'll talk more about these at length when we get to the sections, but I want to at least give you guys a roadmap of what kinds of proofs we'll be doing, what kinds of proof techniques we'll be using, just because this is going to be important, right? I don't want you guys to just see these one by one and go, okay, I remember the things I did in chapter 3, we used only proof by contrapositive for chapter 3. We used only proof by contradiction for chapter 4, and so on and so forth. I think that's kind of disingenuous in showing you guys how we problem solve, right? So in essence, let's talk about our arsenal, our toolkit, and we can look more closely at each of the pieces of our toolkit and what it allows us to do, and then launch into different problem solving stuff where I might give you a question and I'll tell you what to use, and then you should try to see if you can explain why you might want to use one of these over the other. And do keep in mind, if I'm proving something, it doesn't matter how I prove it, right? So like obviously there'll always be one that's an easier way to prove it, but not always. I can think of a few examples where a proof by contraposition and a proof by contradiction go pretty similarly, right? And they're equally easy. And so you can do either and it's totally fine, right? You don't have to pick one or the other. You just want to pick what's easiest for you to figure it out. Right? So again, the rest of this course, we'll keep harping on proof techniques because that's the whole point why I teach this, right? I'm showing you different areas of mathematics, but I also want you guys to start getting used to proofs. And I want you guys to start getting used to techniques which we can use to prove things and understand why does something have to be true, right? How can I prove beyond a shadow of a doubt that something is true? Right, so I think I'll probably stop there today. That's probably a good stopping point. And so just know, I'll send an email out about this, but I think for next week at least, I don't know about weeks after, for next week at least, I think let's plan on meeting, let's plan for meetings on Monday, Wednesday, and Friday. And we'll go from there. Because so far, I think our pace is going pretty well. I haven't gotten a lot of questions on problem, like have a problem session or, requests to like sit down and like work through problems together. So if I don't get any of those, that's totally fine. But that probably means we lose off on the daily schedule for now. So we'll probably say about meeting 3 times next week, and then we'll kind of just see where we're at. And again, if there's anything you guys want me to go over, or if there's anything you think I'm missing that you would like to see before we move on, please do feel free to email me. I'm more than happy to like insert some stuff here.